All right, so thank you for that intro. I would like to start out with some movie clips here. So bear with me, I'm going to be kind of going back and forth between the computer and you guys as an audience. So we'll get this here started right now. Anybody know what movie this is? And unfortunately the audio sync isn't working very well. But this is the part.
We're in the core.
Oh, there we go. We almost hit the end. All right, we're good.
Okay, we got sisters.
Yes. Julie, I can't talk to you right now.
Gotta look
We're right into the flanking line.
I realize that.
You can't attack this thing from the south. We're going to get rolled.
Watch me.
Julie, I know you're upset. You just got to breathe. We both just got to breathe. Cow. I got to go, Julia. We got cows. Another cow.
Actually, I think that was the same one.
All right, we'll stop that one there. So I love that clip. It just cracks me up. So tornadoes have been talked about a lot in the media, both in movies as well as in actual real life. So unlike a lot of science cafes where you have people coming in here and they have like cool things that you can handle, like bones and plants and awesome artifacts, like I can't actually bottle a tornado and show you. I mean, you have little like liquid ones that, they're okay, but not the real thing. So we're going to be watching a lot of video here this evening. And this style here, the Science Cafe, is meant to be kind of interactive. So as we go through, we're going to have some entertaining stuff. We're also going to have some science. So if you have any questions at any point in time, we don't have to wait till the very end. Just raise your hand and try to get my attention somehow. And at a good spot to stop, I will answer your question, or at least try to answer your question. So that's what we're going to do. So that was an example of tornadoes in the movies. We're going to show you a real life example of actual tornadoes. So this
large multiple vortex tornado.
So this is a video caster from
Gary,
one of the local
it's a
news
mile
crews
and
in
a half
Oklahoma City.
Northeast of us right now. This thing is southwest of El Reno. It looks like to me it's moving east. It's going to affect probably south of I-40, about 3 miles right now. Right in front of us, large, multiple, serious. This is a serious tornado, Gary. Large, multiple vortex. This is a big one.
So it looks a little bit different than what you saw in the movie there. This is a little bit more real life here. This tornado went on to produce 300 plus mile per hour winds. Thankfully was occurring over an area where it was pretty
it's going to get bigger.
Pretty rural, so there wasn't a whole lot of damage and very few fatalities actually. So let me pause that here. All right. So let's get into this a little bit here. A nice little primer to make you excited about things to come. Okay. So here are some tornadoes in real life. That video that I just showed you was this really big El Reno, Oklahoma tornado. It's actually the widest tornado that has ever been recorded. It was 2.6 miles wide. Very, very, very large. Winds exceeding 300 miles per hour. That was based on Doppler radar measurements, and there were 8 fatalities, which is actually pretty incredible considering how huge the tornado was and how violent the tornado was. And unfortunately, 4 of those 8 fatalities were actually storm chasers. In a very catastrophic kind of turn of events, they were caught up by a small-scale vortex just outside the main tornado, and their vehicle was flipped and rolled, and they unfortunately didn't make it. There's a second video that I was thinking about showing, but I think for time purposes we'll skip that. But another real-life tornado occurred actually just 11 days prior to the one that I just showed you. That tornado went through the town of Moore, Oklahoma, and interestingly, so Moore is kind of at the crosshairs here. If I can get my little mouse, I'm not going to worry about that. If you look here, so this is one county in central Oklahoma. 3 violent tornadoes went through that town of Moore within a period of 14 years. So I wouldn't want to live in Moore, Oklahoma. I lived actually just south of here in this town of Norman for about 8 years while I was going to grad school. But the Moore, Oklahoma tornado that I was going to show you was about 1.3 miles wide. It had estimated wind speeds that were damage-based, that were exceeding about 210 miles per hour. Unfortunately, as this tornado went through a much more populated area, there were 24 fatalities, 212 injuries, and this tornado hit 2 elementary schools, leveling them to the ground. Hit right at the end of the school day. People were trying to get to their buses. It was a very major challenge. So let's talk a little bit about these tornadoes here. So what exactly spawns these massive vortices? They come from a special type of violent thunderstorm called a supercell. So this is a picture here of a pretty impressive looking supercell viewed from several miles off. So what makes these supercells different from your everyday thunderstorm that most people are familiar with? Well, supercells have a mesocyclone, and a mesocyclone is basically a rotating updraft. And because of that fact, they have a very different internal mechanism that drives these storms and steers them compared to your everyday storm. These supercells can last sometimes upwards of 6 to 8 hours. Your everyday thunderstorm is just going to be basically like an hour, and that's it. So these rotating mesocyclones occur roughly 2 to 6 kilometers above the ground. And they can take on incredibly impressive visual characteristics, like this particular one here. Chasers call this an upside-down wedding cake. You can sort of see probably why. And here's another picture where you have an updraft that's illuminated by a lightning streak there, and you can see the striations in the cloud base there. This whole area in the center here is rotating. It's that mesocyclone. So how do these things form to begin with? That's a really crucial and important piece of information. There are 5 primary environmental conditions that are required in order to get supercells. To get any thunderstorm, first of all, you need to have a warm, moist surface air mass. That's going to provide the fuel for a thunderstorm to form to begin with. And then coupled with cold air aloft, you need this cold air aloft in order to create an unstable atmosphere. Essentially, if you move a chunk of air upward, it's going to keep on going, and it's going to generate a lot of internal momentum. It's going to release a lot of energy as water condenses, and that's what drives the heating mechanisms of these storms, kind of like a large engine. Then a third thing that's perhaps a little bit contrary to what you might think is it's actually very favorable to have a layer about, I don't know, 1 kilometer, 2 kilometers or so above the surface that's actually stable, where the air temperature increases with height. And the reason why this is favorable is because without this, you will get thunderstorms to develop early in the day before you hit the maximum heating of the day. So the maximum heating is going to occur generally around 4 p.m. or so. So if you have thunderstorms that form prior to that, they're going to be weaker in intensity, and oftentimes that's going to create a situation where you just get kind of mediocre thunderstorms that start early and last throughout the day, but you don't actually get a really well-organized supercell to form. So you want this stable capping inversion in order to sort of put a lid on that early convection and enable the atmosphere to heat up and get really steamy before it actually releases the instability to create these storms. Then fourth, if we have this stable layer above the surface, we usually need to have some kind of upward moving mechanism to get that air in motion, to get it past that stable layer. This can oftentimes come in the form of a surface boundary like a dry line, which is a boundary between warm, moist air and hot, dry air. Oftentimes you can also get features aloft, like a small little trough or a little area of energy aloft that gets air moving up to begin with to overcome this little small stable layer. And then most importantly for supercells to form, we need this wind shear. If you don't have wind shear, you are not going to get a supercell. And the wind shear is just a change in the wind speed and direction as you go up with height. So the winds at the surface might be out of the southeast at 10 miles per hour, and then as you go up 1.5 kilometers, they're out of the southwest at maybe 20 miles per hour. And then as you go up another 3 kilometers, they're out of the west at 50 or 60 miles per hour. Those kinds of conditions are going to be favorable for the formation of these rotating thunderstorms. So why exactly is that? So this has to do with the whole essence of forming a mesocyclone to begin with. A mesocyclone is going to form in the presence of this vertical wind shear. So if you look at my hands, my hand represents the wind at two different levels. At the surface, maybe the wind's coming this way. Aloft, the wind might be coming this way. So you get this kind of crossing going on with the winds. And that actually creates this horizontal spin that's oriented kind of like a bike tire. All right? That's fine. It exists kind of naturally in the environment in many cases. But when you get a thunderstorm to develop, what happens is the updraft of that storm, which is basically sucking the warm, moist air from the surface, that updraft turns that wind from being oriented this way to being oriented this way, like a top. And that is what causes these storms to rotate. So if you look at these pictures here, this kind of illustrates one of those horizontal tubes that gets tilted into the vertical by this updraft. And here's a little bit of a trajectory of an air parcel that comes from this side. It's turning horizontally, and then it gets ingested into the supercell and begins turning more like a top. Okay, so where do tornadoes tend to form? We all probably have an inkling of where this happens. Most commonly, it's going to occur in the central United States, kind of in this area here. This is the traditional tornado alley geographic location, but you can also see that Indiana gets some tornadoes to form commonly, as well as, interestingly enough, Florida. So although Oklahoma is, and spanning up into Kansas and down into Texas is most favorable, there are also sort of subsequent areas where tornadoes can form as well. Where do the most violent tornadoes tend to form? Again, you can see this illustrated a little bit here across the Texas, Oklahoma, Kansas area, but there's also sort of this span eastward through southern Illinois and Indiana, even down into Alabama, Mississippi, up into Tennessee, and even a couple in southwestern Ohio, and even one over here in southeastern Ohio. So these violent tornadoes, this is through 2013 from 1950. So they have a little bit less, this is all of them, by the way, so you can count maybe 48 of them or so. So they have a little bit more of a wider span and a little bit less of a kind of concentrated area, although this area here, and this area up in Iowa seem to be kind of favored. Okay. So why is this? Why do we have Tornado Alley to begin with? What is so special about the Central Plains of the United States that makes this area so conducive for these violent tornadoes? So it actually all has to do with the geography of the Central Plains, and perhaps not necessarily in the way that you're thinking. So really what this comes down to is kind of a juxtaposition of a whole lot of favorable conditions all wrapped up into one geographic location. So first of all, the Central Plains are very close to the Gulf of Mexico. So the Gulf of Mexico is going to be a source of moisture. When you have southerly flow up through the plains, you're going to transport the warm, moist air from the Gulf of Mexico upward and northward into the Central Plains area. Secondly, you have an area of elevated land out here in Mexico and in the southwestern United States called the Mexican Plateau. This Mexican Plateau provides an area of elevated, dry, hot air that is oftentimes moved toward the northeast over top of that hot or moist, that warm, moist layer at the surface. And this actually does a couple of things. One, it provides some wind shear in the lowest 1.5 kilometers or so. And then two, it also provides that stable mechanism that I talked about just a few minutes ago here. So this hot, dry air laying over top of that moist air is actually going to kind of inhibit convection from starting too early in the day. Another factor is that you have the Rocky Mountains here off to the west. The Rocky Mountains have this general slope up from the eastern part of the plains toward the western part of the plains, and that gradual slope is very important in driving some features in the atmosphere that are very conducive for forming these storms. One is called the dry line, which I mentioned a little bit ago, and that again is kind of tied also with the Mexican Plateau, which is going to be a surface boundary that separates warm, moist air in the east from hot, dry air in the west, and that can provide a site for convergence where winds can come together and start these storms to form to begin with. And then there's also another feature called the low-level jet or the nocturnal jet. This is an area of enhanced winds that are just above the surface at about, a couple hundred to a kilometer, a couple hundred meters to a kilometer or so. And that can really provide a strengthening of the low-level wind shear, which is crucial, particularly to the formation of tornadoes. And then lastly, we have, or I guess not lastly yet, the Rockies also do have a second role here. And as you have low pressure systems approach from the Pacific, they kind of dissipate as they go over the Rockies. But then on the eastern side of the Rockies, in the western plain states, those lows actually start to intensify. So you get the development of new low pressure on the eastern side of the Rockies. And this happens because the Rockies actually create a topographic barrier. So as air is forced up and over that topographic barrier, it's forced to kind of shrink in the vertical. And if you can imagine a rotating air mass that's going up and it's being forced to squish, it's kind of analogous to an ice skater putting her arms out. So as the ice skater puts her arms out, she's going to spin more slowly. And then on the downslope side, where you start to stretch the air column out because you're basically moving down from the mountains, it causes that air now to be spinning faster and faster, much like an ice skater pulling her arms in. You rotate faster when you do that, when you're converging your mass towards your center point. So the Rocky Mountains provide that low pressure development as well. And that can also enhance southerly flow through the plains, bringing up that warm, moist air from the Gulf of Mexico. And then lastly, we have this large body of land to the north of the Central Plains that's oftentimes very cold. And as the air from that colder Canadian area makes its way down into the central United States, particularly aloft, when you have these troughs of low pressure aloft, bringing that colder air from Canada, and it moves over this warm, moist air at the surface, that provides the necessary ingredients for producing the instability that drives these storms. Okay, so a little misnomer pet peeve, since I'm on a stage here, I want to do my civic duty and tell you that tornadoes do not form from a clash of air masses. If you hear your local news person say that, call them and say, you're wrong. Because clashes of air masses happen all the time. They're called fronts, right? We have cold fronts come through here today. Did we have a tornado? No. So what really happens is it's not the horizontal clash of air masses that's important. It's the vertical, the vertical layering of these different air masses. So next time you hear somebody on the Weather Channel say, and we're having this clash of air masses, which is responsible for a tornado outbreak, you can shake your head and say, man, Jim Cantori, where did you go to school? Sorry. And anyway, so the cold air has to be located above the warm air. All right, so how do we know what we know about tornadoes to begin with? What kind of scientific studies have there been to really evaluate and analyze tornadoes? So first of all, I'd like to talk about observations. There have been a couple of really extensive field campaigns that have grouped together various different observational platforms to study tornadoes in a very kind of systematic way. So mobile radars are often a big component to these field projects. Why a mobile radar? Well, a standard fixed site radar, which is what we have at the National Weather Service here and there, there's one in Wilmington, there's one in Charleston, West Virginia. These radars can't be moved. You can't take the radar anywhere. And most of the time, you don't have tornadoes forming in the local area of these radars. They oftentimes occur, even just 10 to 30 kilometers away from your radar is actually going to degrade the quality enough so that you can't get very good high quality resolution data from these radars. So instead, we're bringing the radar to the tornado via these mobile radars. So there are roughly about 12 or so of these mobile radars in the field currently, and it's kind of plus or minus one or two depending on the year. But these are really important because they can sort of safely and remotely look at tornadoes and the storms around them to detect important qualities of the storm, including things like the wind field characteristics as well as the precipitation distribution. And you can get this in a pseudo-continuous manner, at least temporally and spatially. However, a couple challenges do exist with radars. Most of the time, a radar cannot scan below about 100 meters or so. So a radar operates with a beam that looks kind of like an ice cream cone. So if you're scanning directly in line with the horizon, you're going to pick up debris from the ground like houses and trees and phone poles. So that contaminates the radar returns and makes the data relatively useless below about 100 meters or so, except in special circumstances. Also, you usually can't entirely capture the whole storm all at once with the radar. There's kind of like a give-take relationship with the radar. If you want to look at the whole storm, you can, but it's going to take a long time. And since tornadoes are very rapidly evolving, we don't want to take a long time. We want to get updates as quickly as we can. So oftentimes we sacrifice looking at like the highest parts of the storm in favor of just looking at what's going on at low levels. Another con of radars is that they actually don't detect the true air motion. They detect the motion of precipitation or debris that's in the air, but it doesn't actually look at the air. And as a result, computations that are produced by radar data actually have errors in them inherently because we can't actually measure the winds. And then also, these radars are confined to road networks. So believe it or not, it's actually very challenging to get your radar to a location that's favorable because roads might not work out, timing might not work out. You might be in a great position and have a really great view of the storm and it just doesn't produce a tornado. And then you move your radar to the next location and while you're driving, it produces a tornado. And then while you stop at the next location, the tornado decays and you're left with no tornado data set. So there's a lot of logistics that go on here with mobile radars that are very challenging sometimes to deal with. All right, so some kind of cool radar images here. So this is radar reflectivity. The reds indicate higher values of precipitation, more reflective things and targets in the sky. These are supercells on radar. So a typical supercell on radar is going to kind of have this hook kind of shape. So it looks maybe like a fishing hook or an eagle with a beak down here, something like that. So you have air coming into the storm over here. You have your updraft in this location here, and then you've got air that's kind of wrapping around the backside here. And the tornado is going to generally occur roughly around this spot right there, kind of at the interface between this inner part of the hook and the updraft there. So what we're seeing on here is this area right here. If you look really closely, you might be able to see there's this little like yellow-white dot here. That's a tornado. So what's happening in here is the tornado is spinning so quickly that it's actually centrifuging the precipitation out of the tornado center. So you have this little empty spot right there. Similarly down here, and this radar unfortunately is suffering from what's called attenuation, which is back here where you don't get a very strong signal because the rain is so strong as the radar beam passes through it, it essentially extinguishes the signal. But you can see some pretty cool things here, some pretty cool structures. We've got these spiraling bands here, and again, you see that little eye of the tornado located right here. And then here's another image of a tornado. The tornado is located right here. This is very close to the surface. We actually don't see the eye very close to the surface. We see that a little bit above the surface because at the surface immediately you have so much debris that's contaminating the radar beam that you don't end up seeing that weak eye area there. All right. They are radar shots from the ground. So in this picture, the radar is right here in the center. In this picture, the radar is down here. In this picture, the radar is right here. So anywhere from in this picture, I think it was about 7 miles away. In this picture, it was about 3 miles away. In this picture, it was like a mile away. So great question. Any other questions, by the way, now that we have a good little stopping point here? Go ahead.
I know that you touched on this in your environmental factors contributing to the tornado occurrences slide, but I was wondering, are the things that make supercells so strict that they cannot, like, if you have something that's slightly different, like say, China also has the kind of, you've got the cold, you've got the mountains, you've got the warm air from the Pacific. Is that not close enough, or are they very strict?
So the question was, are the parameters regarding tornadoes so strict that you can't have them geographically other places? You can have tornadoes geographically other places, and you do. Canada, our neighbor, has tornadoes also, and they're also very common in Burma and like south of the Himalayas area there. And there are tornadoes that do happen in China. The challenge is that you oftentimes don't get the conditions to occur together at the same kind of frequency that we get in the Central Plains. Yeah, great question. Anything else before we move on? All right. Okay, so talking about observations, we also have these mobile mesonets, which are basically minivans or cars that are equipped with a variety of instruments that are designed to take samples of the environment of pressure and moisture and temperature and wind speed and wind direction. The idea is to sort of travel roads, kind of commonly just going back and forth as a tornado approaches to see how these conditions change both in time and with space. So these are good, but again, you're confined to a road system. So where there are no roads, you can't take these. And oftentimes, the road networks are relatively scarce in the Central Plains areas. So you can get a few good observations, but oftentimes, there's not a whole lot of spatial continuity there. Another option is to use these stick nets, which are basically like tripods that are equipped again with various different instruments. And then this little thing is called a turtle or a pod. It gets basically deployed close to the tornado with the idea that the tornado passes over it. This guy, Tim Samaras, designed this himself. He's an engineer. Actually, unfortunately, he was one of the 4 people that was killed in the El Reno tornado in 2013. But you design these instruments and deploy it and hope that it gets hit by a tornado to observe pressure trends and so forth. Yeah? This is not anchored to the ground. The turtle is basically designed to withstand, as the wind comes over it, it has a physical downward force so that the turtle itself does not get moved around by the wind. The tripods here, these stick nets, are anchored to the ground. All right, so here is a pressure trace from one of those probes, the little turtles, that was hit by a tornado. So you can see there's a dramatic pressure fall of over 100 millibars. So this is very, very dramatic. This is lower pressure than hurricanes and than really anything else that we can experience on the planet. So very low pressures within the center part of a tornado. There have been, again, as I mentioned, these kind of coordinated field campaigns where you have a variety of these different instruments that are being deployed all together. This was the Vortex 2 field campaign that was in 2009 and 2010. You can see a whole suite of instrumentation. There were about 9 radars here. We had like 12 mesonets and a whole bunch of stick nets and a whole bunch of little pods designed to basically smatter the whole area where a tornado ideally was coming and get instrumentation out there and observations. These are the decision makers who were trying to figure out where to go, what to do, etc. You can argue about how successful that field campaign was, and we won't do that today. But some challenges that I kind of already made some of these with observations. Obviously, there are logistical issues with observations, things that you can't control, road networks, visibility, storm motion, timing, etc. But there's also human choices that are involved here. Where exactly do you go? What decisions are you making? Which storm are you targeting? So there are these sort of decision trees that can result in errors and don't end up getting you the observations that you want. You can also have instrument malfunction. It happens all the time, way too often than you would think, way too often than what is convenient. Additionally, you can't retrieve 3-dimensional data of particularly temperature and moisture. We just don't have that capability, and that is a huge, huge problem with trying to figure out and unravel the mysteries of supercells and tornadoes, because that temperature data and moisture data plays a vital role in the storm formation and in the dynamics driving the storm. Yes?
The iconic scene, the investigators introduce a pod that has the aluminum can. Is it common practice to ever introduce debris or sensors into the visible storm?
Right, so the question was, is it common practice to introduce a sensor or a debris source into the storm? No, that has never officially been done. However, the Dorothy pods in Twister were actually developed off of a real scientific prototype called Toto, which was the Totable Tornado Observatory. And that thing looked very much like Dorothy did, except it didn't have the little whirly birds that came out the top. I don't know if, I think realistically the cost benefit risk analysis of deploying an instrument like that is probably too great that you would, unless you are independently wealthy, you probably would never get that funded through NSF. But it hypothetically would be pretty cool. Okay, so there are problems with observations, ultimately, is what this comes down to. So we oftentimes turn to computers then to answer the problems that we can't answer with our own eyes and ears. So this is also done in meteorology, and particularly with regard to tornado studies. So there are a group of scientists that specialize in generating tornadoes within the context of a computer program. So these are computer simulations or data assimilation where you actually take observations and put it into the computer model and make the computer model kind of conform to those observations. And the good thing about computer simulations is that as the user, you have complete control. You are essentially playing God when you're using these computer models, and you can tweak parameters as you want, and you can say, all right, well, I'm going to jack up the instability a little bit and see what happens. I'm going to change the wind shear profile a little bit, see how that changes the storm structure, see how that changes the precipitation distribution. So in that sense, it's very cool so that you can kind of get a feel for what changes have impact on your storm. It also is very beneficial because it has continuous, both in time and space, continuous data resolution. So you run your model and you have a full, complete data set from start to end of that storm, which is really unprecedented in the real world. However, the downside is that there are never really 100% real computer simulations. There are always sort of assumptions that kind of have to go into them, and things like, am I going to categorize this precipitation target as hail or as an ice crystal or as something called grapple? Something that simple actually has dramatic effects on the outcome of your computer simulation. And we just, microscale processes that are occurring almost at the atomic level actually have implications. So these unfortunately are never 100% quite real, but they're pretty darn cool. So I'm going to take a second and show you some footage here of an actual computer simulation that a colleague of mine did. So this is a simulation developed by a guy named Lee Orff. So this is all done within the context of a computer model. So you have a really great looking supercell cloud here, you get inflow coming in, you get the development of a wall cloud, and you get the development of a tornado, or a tornado-like vortex is what they actually call them because it's within a computer. So it's not a real true tornado. And then you can see some precipitation start to wrap around and be ingested into the tornado. Very realistic looking behavior here. And you can do really cool things like this, with this, look at the vertical winds and look at the rotation. So here we're looking west toward a supercell. This is an updraft here. You can see an area of horizontal rotation that's basically being turned into the vertical by the mesocyclone. This red tube right here is more or less a tornado. And then you'll notice there's a blue anticyclonic partner to this particular tornado here in this simulation. So again, let me loop that one more time so that you can sort of catch that again. So again, really pretty cool looking things. So what you can see here is rotation is sort of developing along this forward line here, and then it's being turned upward. Some of it gets kind of wrapped around into the area where the tornado is forming. Okay, so this brings us to the next, oh yeah.
How long does it take to run one of these simulations? Does it take a long time to crunch all the numbers by the system?
Yeah, how long does it take to run a simulation? It depends on the resolution of the model. So that model that you just were looking at had 30-meter resolution. So it has grid points every 30 meters, both in the horizontal and in the vertical, over a domain of, I think, 20 kilometers by 20 kilometers by maybe 10 kilometers. To run a simulation like that takes about 4 days. So lots of number crunching, even on a supercomputer. And then you get the results, and you look at the results and realize, oh, something wasn't right in my parameterization, and I have a totally unrealistic storm, and I've got nuclear explosions going on, more or less. So yeah, there's a lot of challenges, and then you have to reset and rerun again and try to hope that something different happens the next time. Any other questions? All right, so moving on, how do tornadoes form in the first place? I should rephrase that question as, what do we know about how tornadoes form in the first place? All right, so what we know is that we need to have a strong low-level mesocyclone. So traditionally, as a supercell is forming, a mesocyclone is going to be between about 2 and 6 kilometers in the vertical. At some point in time, things kind of change a little bit in the way the storm is evolving, and you start to ingest some sort of extra rotation into that storm, and you need to get this rotation, the mesocyclone, to actually lower a little bit and be between, maybe 500 meters to a kilometer or so. That's absolutely critical. So the reason why that's critical is this enhanced rotation actually generates a localized area of low pressure where that rotation is. And underneath that, where you have slightly higher pressure, you actually have an upward directed force that's going to cause air to move upward. And that's really only efficient if you can have this strong low-level rotation to begin with. All right, so then additionally we need to form this horizontal rotation that occurs along what's called the forward flank here. So this is sort of the east-west oriented boundary that separates the rain from the supercell, or the rain of the supercell, from environmental air to the south here. So we get this spin, and then we need that horizontal spin, again oriented kind of like a bike tire, to be advected around, transported around into this area of the storm here, all right? That needs to happen. And then additionally, after that happens, we need to transport this horizontally spinning air, which is a couple hundred meters or so above the ground. That needs to be transported downward. So we need to have this rear downdraft in these supercells to actually create downward motion and get that horizontal spin kind of tilted down and be oriented in the vertical like a top. So this downdraft is referred to as the rear flank downdraft, and what happens is you get this circulation that spins up between rain-cooled air over here, warm air that's more buoyant up here, creates this rotation, gets moved into this area where the mesocyclone is, it hits the downdraft, and then the downdraft basically moves that air downward and then can tilt it into the vertical. And then as you get that air that's tilted into the vertical, as that encounters an updraft that's generated by that low-level mesocyclone, it can stretch out and get really fast, and you have a tornado. So that is, in essence, what forms a tornado. All right, so question, is this a tornado? Okay, if you say yes, raise your hand. I know my students will say yes. If you say no, raise your hand. And now I give the answer away, so nobody's going to put up their hand and say, this is indeed actually a tornado. So despite having a condensation funnel, this black part, that's not all the way at the ground, if you look closely, there's this sort of like hazy stuff going on down here. That's actually dust that's being picked up by the rotation on the ground. So your eyes are actually visually not very good at telling you whether or not there's a tornado on the ground. All right, so that's the little dust thing. All right, so we have this theory, and let's kind of talk about more specifically about the tornado. How do we get this tornado itself to form? What happens with this rotation with both time and height to get these tornadoes to form? Well, there are two classic theories that exist. One is called the top-down process, also referred to as the dynamic pipe effect. And this is where you have rotation that's strong at kind of mid-levels, not truly mid-levels, but above the ground, kind of maybe the lower part of your cloud. And then it gets stronger, and as air gets moved upward into that updraft, that air converges, it spins faster, and you have this slow downward progression of the vortex from mid-levels to the ground. And that generally is thought to occur on the order of about 5 to 10 minutes or so. All right, so let's take a look at an example of tornado formation here. All right, so if you can't see, there is actually a funnel cloud right here. It's kind of starting to descend a little bit here. You can barely see the ground periodically. You can see it sort of looks like that that funnel's getting a little pointy. It's kind of starting to go down to the ground a little bit. Storm chasers are getting excited. Feels like an eternity as you're watching this. All right, and there it goes. You can see that condensation funnel work its way down. It's trying so hard. Now look at the ground. It doesn't really look like anything's happening, right? So just about there. And there we go, more or less. All right, so yay, tornado, you did it. All right, now there's a second theory also about tornado genesis, and this is referred to as the bottom-up process. So in this process here, what happens is you have strong rotation that is closer kind of to the surface, and you get convergence that causes that rotation to really kind of build almost simultaneously, either from the ground up or kind of contract mutually together at a very rapid pace here. So originally it was thought that supercell tornadoes formed by this first mechanism, and then another type of tornado called a landspout formed from this second bottom-up thing. But there's a problem here, all right? So we know that tornadoes can actually form very quickly. All right, observations tell us we can go from something like this to like this. If you look at the timestamp, 2051, this is 2055, 4 minutes between this and this. An additional problem is that traditional radars can't scan very quickly. Most of the Weather Service radars take 4 minutes to complete an entire scan of the atmosphere. So this is a problem because we don't have the capabilities to really observe these processes very well. All right, so we introduced a new rapid scan radar. All right, and this was part of my PhD work, was to work with this radar and to look at a couple cases with this radar. So I put together a case of a tornado that formed in 2011. It was rated an EF5. And when I looked at the vorticity associated with this tornado, what we ended up seeing is that you had a little blip almost at the ground. 15 seconds later, a little blip a little higher up. 15 seconds later, a little blip even higher up. And then smack right at tornado time, you get a full vortex to be present within this time difference is about 30 seconds. So you go from no tornado to tornado in 30 seconds. All right, I'll skip that slide here. Another conflict, we have this picture of a tornado. 230225 is this tornado. The NWS start time for the tornado, as well as the radar indicated vertical coherent vortex, was 2304. This funnel cloud was 1.5 minutes prior to that time. So what exactly is going on here? Well, this tornado, I'm going to skip through these animations here. I'll talk about one. All right, so this one right here is roughly that time of that image. If you look, yellow means movement away from the radar, which is located over here. Blue is movement toward the radar. You have circulation occurring right here. This is at essentially the ground. This is 10 meters. This is 300 meters. Wide circulation, but it's not close together. So I did a little bit of a study to see exactly when you get this tornado vortex to form at different heights. And what I found was that the tornado vortex first appeared at essentially the ground, 10 meters, again, about 1.5 minutes prior to that vertically coherent vortex, which occurred at that point in time. So our eyes may deceive us, is the bottom line. Additionally, radar data might deceive us. I didn't get to really talk about it, but what tends to actually happen is you get these sort of transient little spin-ups that show up and then go away, show up and then go away. And a radar can actually, if you don't have high enough temporal evolution or resolution, a radar could think that that's all connected to one tornado, when in actuality, it isn't. So these are just 2 supercell events that are now present in a growing number of data sets. So we're at about 12 now of supercell tornado genesis. That does not form from the top down, even though your eyes see it that way. So it really calls for a change in the paradigm of how we think about tornadoes and tornado formation. Okay, so kind of quickly here, I know we're running out of time. What do we still need to know? Well, we really need to know the ultimate source of this near ground rotation. So where is this rotation that came with that low level tornado circulation? Where is it coming from? We don't have a conclusive answer to that question. So I'm going to skip that image unless we have time to go back to it later. So what else do we need to know? We need to know what role friction is playing. That is a big question mark right now. Most model simulations neglect friction entirely. And when they don't neglect friction, the newer ones are saying, oh, wait, friction has actually a really big, important role. And it's not being fully exploited right now or investigated. Additionally, why does one supercell produce a tornado and another one, like 20 miles to the north or 20 miles to the south, not? And then how can we, with any skill, forecast when a storm is actually going to produce a tornado? So just about done here. This is my last slide. I'll give you a little thought experiment. Which of these storms is going to produce a tornado less than 5 minutes after these images here? So we have radial velocities in the greens and yellows. The radar is located at various different spots, but basically when you have blues next to yellows, that's going to indicate rotation. This is showing you the hook echo. This is showing you the hook echo, hook echo, hook echo, hook echo. All right, so think about it a second. How many people think this is going to form a tornado in 5 minutes? Raise your hand if you think yes. Okay, a few. How about this one? Okay. How about this one? Okay. How about this one? Okay. And how about that one? All right, let's see the answers. Yes, no, no, yes, yes. So you can't really tell in most cases. All right, so I will end my official presentation there, and at this point, take questions. Yes.
Do we have data now that allow us to kind of forecast super tornado outbreaks? I ask this because when I was a little kid, I was out in the yard about noon in Wichita, Kansas. Real humid day, and it's kind of the most dramatic atmospheric conditions I've ever witnessed. And then later in the afternoon, the super outbreak occurred about 2 states east of Kansas. Mm-hmm. But there was a dramatic kind of wind gust front came through, and then you could see that. I mean, I've never seen the clouds racing as fast, in the sky, in opposite directions.
Yeah, that's
the most dramatic kind of skyscape I think I've ever seen.
Yeah, absolutely. So the question was, do we have good enough data now to be able to forecast like super outbreaks? And the answer is yes, absolutely, to an extent. So we know the large scale and even some of the smaller scale environmental conditions that are required to produce tornadoes. We have exceedingly good skill in most situations at predicting these very large outbreak type events. The more complicated question is where within this, 1,000 square mile area, where are you going to have the most damaging storms? Which storms are going to produce the tornadoes? Is it going to be in this county or is it going to be in that county? Those types of questions we can't answer yet, but we do have a much better feel than what we did 30, 40, 50 years ago about when we're going to have those large scale events. Now the small scale events still sometimes can be a little bit more elusive and sometimes more contingent upon specific local conditions rather than larger scale ones. All right, what else? Okay.
Are water spouts, if I'm using the correct term, are they mini tornadoes?
Are water spouts mini tornadoes? Yes, they are. Actually, water spouts generally are forming on a gradient between cool temperatures associated with water and hot temperatures associated with land, which creates which creates spin that gets oftentimes kind of condensed by a convective updraft and forms a water spout. Commonly, they just sort of stay over the water in that area where the temperature gradient is located. However, they can sometimes transition onshore, and if there's a thunderstorm overhead, they can transition into actual like tornadoes on land. Other questions? Yes?
Is the energy from the heat of condensation?
Is it? Yes. So the,
How do you power this thing?
yeah, so
What is the temperature gradient in a funnel?
that's a great question. So the question was, what's the energy source for these tornadoes, and what's the temperature like within the funnel? So the latent heat of condensation is going to be what's basically powering your supercell. So that is the energy, the engine that's driving the thunderstorm itself. Within the actual tornado, it is not. Within the tornado, it's less of a thermal instability and more of a shear instability. So it's more about the actual properties of the wind field compared to the actual properties of the temperature field. What is the temperature like inside the tornado? We have very few samples to actually tell us that. Yes, we do. That is true. We do have the models. I have never actually read anything that specifically addresses the perturbation temperature within a tornado, but I do know that there is some evidence to suggest that you need it's kind of like a Goldilocks problem. Like you need just enough cold air to get rotation to sort of develop between the contrast of warm environmental air and rain-cooled air within the storm. But if you have too much of that, then it basically wipes out the storm and you get so much cold air that it blows past the rotation area and moves forward into the environment and actually is not conducive. But if you don't have enough of that, then you're not generating enough rotation kind of along that forward edge to be tilted up into the vertical and form the tornado in the first place. Other questions? These are great questions, by the way. Okay, go ahead.
Do you mind if I ask two?
I don't mind.
So my first one is kind of just a kind of technical thing. Because I know when I was younger, at least, they would always classify them as like you've got an F5 or an F4. But now a lot of times I hear them called EF. Like, was that because there's worse storms, you have to have a bigger range, or was that just because we have like better data to like further classify them smaller?
That's a great question. So the question was, what is the difference between the F scale tornado scale and the EF scale tornado scale? So historically, the F scale was proposed by Ted Fujita to be a damage indicated estimate of wind speed. So you would look at specifically a well-constructed home that a tornado impacted, and you would look at that well-constructed home to determine, is the roof off? Are the walls intact? Are the walls not intact? Do you have any debris around the home, or do you essentially have a clean slate with a foundation left and that's it? The problem with the Fujita scale was that it was only based on well-built homes in the 1970s. So building practices have changed. Very much so, construction practices have become more efficient and cheaper. And what was a well-built home in the 1970s or would now basically be a bomb shelter in the year 2000. So we have these issues with changing construction practices. Additionally, what happens if you have a tornado that goes through a downtown city district where there aren't any houses? What happens when you have a tornado go through a cornfield? So what they ended up doing is they grouped together a whole bunch of meteorologists and engineers and both structural engineers and wind engineers, and they got a whole bunch of really smart people together to sort of figure out a new way to do this. So they extended that F scale and revamped it and renamed it the EF, or Enhanced Fujita Scale, which includes now about 32 different damage indicators, including things like Walmart, telephone poles, trees, the mini-mart gas station awning. So things like that, so that we can have a little bit more of an extensive kind of indication of the damage. And it also bumps down the wind speed. So what used to be associated with an F5, which was winds greater than about 280 miles per hour, now an EF5 is associated with wind speeds greater than 200 miles per hour. Does that mean that the winds are changing? No, it means that we can't determine damage any more than about 200 miles per hour. After 200 miles per hour, everything is so obliterated that we can't discern 200 miles per hour from 300 miles per hour. Great question. And then you had a second one?
Yeah. I know I asked earlier about the requirements for a supercell forming, but I was wondering, because with the climate changing like it is, would this potentially cause if the conditions are like strict enough, is this going to cause the tornadoes to, like the worst ones, to move north? Or
So what will happen with tornadoes in a climate change scenario and a climate change environment? The answer to that is what we currently know. So tornadoes are very challenging in the sense of a climate scenario because they are so small, and climate models are operating on space scales that are considerably larger than what a tornado scale is. What we can say is we can look at the environmental conditions that we know happen when we have tornado outbreaks particularly, and we can say how are those environmental conditions changing in time and space. So what we've been able to determine is that from year to year, there's most likely going to be a larger amount of variability. So some years you have nothing, and then other years you have these super outbreak years where you just have hundreds of tornadoes occurring. That's one thing. Another thing is you may actually end up having fewer tornado days. So across the calendar year, you might only have 5 tornado days, but those tornado days are associated with more violent events. So that's basically what we know. We don't have quite enough information to determine a geographic trend for that yet. I mean, hypothetically, perhaps it would make sense to have things kind of transition a little bit further north if your jet stream is moving to the north, but I don't have a good answer for that. Go ahead.
I was just wondering, just like a general question, do you think with all of that technology and simulations that we'll ever find out like any ways to brace structures or make it like, you know, other than just jumping cover for people, do you think they'll ever find like more accurate ways
They exist. It's just that the cost benefit, the question is, will they ever come up with ways to better prepare, predominantly through a structural sense, for these tornadoes? And the answer is that these ways and these mechanisms exist. The problem is that people don't want to pay for them. And if you are looking for homes in a neighborhood where everybody's house is $140,000, and then you go through and you do all of the double reinforcements, and you make your windows extra safe, and you put your extra large tornado shelter in, your home is going to cost $200,000. So are you going to be wanting to pay $200,000 when your neighbors are paying $140,000? Okay. So I believe we're out of time here. I'm sorry. If you have individual questions, you can come up and ask me at this point. So thank you so much. You guys were a great audience.